Hi, in this video I'm going to show you how to calculate a power spectral density, both with our NDAC open source Python library, as well as showing kind of what's happening under the hood in a generic power spectral density. And then I'll conclude with how to calculate a power spectral density on another real world test data set. So this is part of a 4-part series, so please subscribe to check out the other videos on FFTs, comparing them and analyzing recordings that have varying frequency content. Again, this is using our open source library, which you can download for free. You can do pip install NDAC. I'm installing a development branch, so there's more features in it, but it's open and I encourage you to do that. So I started by generating 3 signals. One is noise content from 10 to 50 hertz. It's hard to see in the time domain. The other is adding 2 sine dwells or sine tones on top of each other, one at 30 hertz and one at 80.25. Again, it's hard to see in the time domain. And then I added the sine dwells onto the random. And again, engineers typically the first thing they do when they get data is plot it in the time domain, which is good. You get some sense of what's going on, but it doesn't tell you a whole heck of a lot. The next step is to do some frequency analysis, and that's where the power spectral density is really valuable, especially for data that has random content, content across many different frequency ranges, which is most often, every real world vibration application. So using our open source library, it's ndac.calc.psd.welch. So there's a variety of different functions in calc.psd. Welch's is the primary way to calculate the PSD. We're passing in here the data frame, the data that has the acceleration data indexed by time, and then we're specifying a bin width of 1 hertz. And the output now is a data frame with an index of 0, 1 hertz of frequency content, and then the values for each signal. And now I can plot it. And you see here the noise is nice. We have a kind of flat line here from 10 to 50 hertz. With the sine dwell, we see peaks at 30 hertz and 80 hertz. It's not exactly at 80.25 because I'm specifying my bin width to be at 80, and then at 81 and at 79. So the other element here is that it's a slightly lower peak because it's kind of leaked into other bins. It's not exactly centered on my bin width, but really good. The other problem here with the PSD, though, I'm seeing when I'm looking at a sine dwell or a sine tone is my value here, G squared per hertz, isn't as intuitive maybe as you're used to. It's a density, and we'll get into that more in the comparison video, but something to call out. And then the sine on random, you see the flat line and then the peaks on top of that. So here I did a little bit of going through all of the different time ranges and three different bin widths to show you how the PSD looks for varying time ranges and bin widths and varying signals. And focusing here on the random data, that's this column here, what you can tell is the values are all about 0.02, 0.03 G squared per hertz, regardless of my bin width. As my bin width gets wider, if I just focus on the full time range, as my bin width gets wider, this becomes more averaged, and we'll see that as we explain how a PSD is calculated. But even when I do the short recordings, maybe this recording, it's a little noisy here, especially, but you can tell it's about the same value. And that's really the power of the power spectral density, is the outputs, the values that come out of it are independent of bin width and time duration, which allows you to compare recordings to one another. That's why it's used for quantifying vibration signals and used by test standards. So that's really good. Now, if I look at the sine dwells, you'll notice that as my bin width gets wider, so it goes 0.5 hertz to 1 hertz to 2 hertz, my value goes down. And that's because it's a density. So as my area, if you will, is getting wider frequency range, there's less frequency content spread across that whole frequency range, this wider range. But as I narrow in exactly on that sine dwell, it has a higher density of energy. So big takeaway is it's really, really, really good for random content. It can sometimes mask, though, sign dwells, and so we have to be a little careful, but it's really, really good for random content. So how is the power spectral density calculated? Well, there's a couple steps. The first thing that happens is the time duration is segmented, and typically there's overlapping segments, and I'll show you that in a second. There's window functions that are applied to that. Then and a Fourier transform is calculated on each of these segments. There's the output is squared and normalized to the frequency bandwidth, so that length of the segment now no longer matters, and then you average them all together. So let me show that in action. Here's my 10 seconds, and I specified all these 19 different segments because they're all overlapping by 50%. So here's my 0 to 2 seconds, my 1.5 to 0 to 1.5 seconds. No, sorry, 0.5 to 1.5 seconds, 1.5 to 2.5 seconds, 2.5 to 3.5. But then you notice, again, there's another segment that spans the two, so they always overlap. You'll notice that each of these have this kind of, they taper up and down. It's because we applied a Hanning window, and the Hanning window is really helpful in terms of not allowing frequency content to leak basically into other frequency ranges. So that's the first two steps: segmenting the file, having overlapping segments, so you have more chances, more segments to kind of calculate the Fourier transform on, and then applying the Hanning window. Then you compute an FFT, a Fourier transform, for each one of these segments. I plotted here as a waterfall plot, again using our open source library, which is waterfall plots are normally used when you have varying frequency content, and we'll see that in another video. But you can tell here, they're all about the same, and I'll show you a different plot. But this is kind of the fundamental element of the PSD, though, is there's all these segments and FFTs per segment. And then we can plot all these segments together here now just in this axis, and the power spectral density then averages them all together. And so the result is this nice clean one, even though at each individual segment's really rather noisy and messy. But when it's averaged all together, you get a really nice result. There's another way to calculate this using a couple functions in our library, rolling power spectral densities to explicitly segment different times, as well as to see how things change over time. We'll get through that in another video, but I wanted to include that here, and you get the same result. And you can plot that as an animation over time. But the point is, every segment may be a little different, averaged together, really nice, clean result. And that's how you calculate a power spectral density. Let me demonstrate that same thing now with some real world data. So I'm pulling in some data from a train passing over a bridge that was one of our Guess the Vibe segments. Here's the acceleration data. You see there's timestamps and then the 3 channels of acceleration data. There's a lot of data in here. I was sampling pretty fast. Those over 1 million samples in this 10-second recording or a couple second recording. And here's as the bridge passes by overhead. If I zoom in here, it's, I'm going to actually explicitly define, I only want to look at the time 2112 to 2116, so just when the train's actually passing overhead. I'm going to plot the time domain just for a tenth of a second here so you could see it. A lot of different content here, and again, this is representative of real world data. It tends to span across a lot of different frequency ranges. So let's see that in the power spectral density. Again, calculating power spectral density is super easy. Just pass in the time data, and I specify the bin width. I like doing a bin width of 1 hertz, but it's up to you. And then here's my power spectral density, and here I can plot it. And so looking at this, I'm going to maybe focus on the Y. I know there's some peak frequency around 23 hertz. Maybe that's a fundamental mode of the bridge. Not quite sure. Maybe it's the could also be the wheels, the rate at which the wheels are turning on the tracks of the train. And then there's a lot of other frequency content. Some of these are resonances, some of it's just random. But you get all that in the power spectral density. What may be problematic though is there's still a lot here. This is still plotting over 10 kilohertz. So there's 10,000 points. If you want to put this into a simulation, it's a little cumbersome. And because power spectral densities are densities, I can get wider ranges. And you could just do that in a linear scale, like by specifying a bin width of not 1 hertz, but maybe 20 hertz, or a bin width of 80 hertz, which would be pretty extreme. Or you can convert to an octave spaced range, which is typically what's done, especially because you plot power spectral densities in a log scale also. So it'll be evenly spaced in logarithmic space. So we have another function here where you give the PSD2 octave. The input is the linear space power spectral density, and then you specify your starting frequency and how many bins per octave you want. And so I went really coarse with just 1 bin per octave. So every frequency is 2 times the last frequency. Most often people will use 3 bins per octave, 6, maybe 12, but you can play with that. And now I plot that, and you have a nice, more kind of more representative or more summarized characterization of the vibration environment as the train went by. And this would be really easy to provide to a colleague or provide to a simulation to then simulate that bridge moving as the train went by. And that is how you calculate a power spectral density, again, using our open source library, but also you now hopefully know the fundamental kind of steps that go into calculating power spectral density. Again, please subscribe to our videos, and you'll see some other videos showing how to analyze vibration data in the frequency domain. Thanks.